Okay, it's a photo finish, but we're ready. So let's go back into the main room and yeah, see you in there. Good evening, everybody. I'm Jared Stewart, the Strategic Communications Manager with the Mount St. Helens Institute, and I'll be your host tonight for Views and Brews. Thanks for joining us. It's the first Views and Brews of 2023, and events like this are made possible by donors like you. So if you find what we do resonates with you and you feel moved tonight, please consider making a donation via the link that will be posted shortly in the event page. The Mount St. Helens Institute is the official nonprofit partner of the Mount St. Helens National Volcanic Monument. We work to advance understanding of the Earth through science, education, and exploration of volcanic landscapes. Our program season is just around the corner. We've got a lot going on this year. Our education team is currently accepting GeoGirls applications. GeoGirls is a 5-night science camp for girls. It's free to attend thanks to grants and donors, and applications are due by April 1st. So if you know a student who'd be interested, let them know, and you can find those links on our website. If you want to get out and explore, have some high adventure, and learn about Mount St. Helens, there's no better way to do that than through one of our guided adventures. Winter trips to June Lake are happening next month, and spots are filling up fast. If this summer you can summit the volcano, get an up close and personal look at Crater Glacier on our Glacier Overlook hike. You can take in great views from Harry's Ridge on an eruption hike, or spend the weekend with us on our popular Into the Crater trip. All these trips not only get you to some amazing places, but our expert staff can provide you the rich ecological, geological, and cultural context for what you're seeing and experiencing. It adds a lot of depth to the landscape. Finally, I'd also like to note that the Mount St. Helens Institute is a proud partner of the Cowlitz tribe, and we encourage you, wherever you are, to learn about the indigenous cultures where you live. We work on the land of the Cowlitz and the confederated bands and tribes of the Yakima Nation. It's the legacy of an ancient people in Southwest Washington. It's rich with descendants who occupied a vast territory in this region prior to European exploration and confiscation of these lands. And these folks continue to thrive today. So please keep this in mind as you come to Mount St. Helens and experience the landscape. Let's get to tonight's events. If you have questions while you're watching, please feel free to ask them in the chat feed, and we'll get to as many as we can at the end. Our presenters tonight are Megan Collins, Nayoung Her, Sonia Niemanen, Haley Bogle, and Catherine Moore Powell. And they're with the Mountain Rain or Snow project. It's a community science project that believes direct observations made by people are the most accurate way to discover how precipitation phase varies in time and space. Tonight, they'll share with you what they've learned so far in collaboration with 1,100 plus observers nationwide who keep their eyes on the sky during winter storm. Folks?
Thank you so much, Jared. We are so happy to be here collaborating on this event. I'm going to get some visuals up for you all so you can see. Just give me 1 second to share. So as Jared said, my name is Megan Collins, and I am really proud to be part of the Mountain Rain or Snow team. I am the first of a total of 5 speakers. We're going to be giving little lightning talks here tonight on the topic of Mountain Rain or Snow, which, as Jared mentioned, is a collaboration with community observers to better understand winter storms. And if I were to summarize this whole evening in just 30 seconds, I would say that our own eyes, you and I, do a better job than current satellite technologies and other weather monitoring technologies at answering the question, what is falling from the sky right now? When it comes to winter storms, this matters a great deal because an inch of rain is very different than an inch of snow. And we're particularly interested in that question of what is falling from the sky right now in the little temperature zone right around freezing. And we're going to talk about really what that looks like. So tonight, as I mentioned, you're going to hear from 5 of us on how mountain rain or snow citizen science is really driving advancements in a number of technologies that we use to power our weather monitoring and weather forecasts. These are the advanced technologies that are behind the hydrologic and meteorologic estimates of the things that we rely on every day. So thank you so much for joining us tonight. The Mountain Rain or Snow project really begins with this phenomenon. Have you ever noticed snow falling when the temperature is above freezing? This is not a challenge to the laws of physics, but it can be quite confounding to satellite and other technologies that track our weather. And we'll hear in a few minutes from Sonia, Nyang, and Haley about just how this phenomenon is pretty challenging for our technologies. First, I want to dive into what's behind this phenomenon, and then we'll unpack what we're doing about it. So as you can see on this graphic, the transition between rain and snow, which is really what we're interested in as part of this project, can differ depending on humidity level. So water consistently freezes at 32 degrees Fahrenheit. But the reason that sometimes we see snow falling a little bit above freezing can be that we're in a slightly more arid environment. So it's partly driven by humidity in the air. And as crystals fall from the colder layers of the atmosphere down to warmer layers, they may just melt a little bit more slowly in less humid environments. And this can change depending on what mountain range you're in, elevation, and so on. So the rain snow line and the temperature at which rain shifts to snow might differ from region to region. And that is why Mountain Rain or Snow is working with community observers across the entire continent to track winter weather. And this all matters, like we said, because our satellite technologies rely on really accurate estimates that are calibrated to weather. So we mentioned before that our human eyes are really the best way to differentiate between rain, snow, and mixed precipitation at freezing. And because satellites don't always get it right, we're asking for help so we can make improvements to those technologies. So the overall goal of this project is to better monitor the phase of precipitation during winter storms across a range of hydroclimates. As we proceed this evening, keep an ear out for the following things. You'll hear from Sonia about how ground-based observations are really an excellent standard against which we can measure the performance of numerous technologies that monitor weather. You'll hear from Nyang about how we created a report card of sorts about the ability of NASA satellites to track or estimate precipitation phase. And then Haley's going to go into that a little bit more deeply by exploring how certain satellite technologies do when it comes to atmospheric river events and non-atmospheric river events. And Catherine's going to bring it all together by explaining what these advancements and these technology assessments or performance assessments that we've been doing, what they really mean for the scientific community. And then at the very end, I am going to invite you to participate and explain how you can get started. So with that, I'd like to introduce Sonia, who is going to get us started with a comparison of different weather technologies.
Thanks, Megan. So hi, everybody. I'm Sonia, and I'm going to be telling you about research that the Mountain Rain or Snow team recently completed that looked at how well different tools do at partitioning snow and rain in the Sierra Nevada. So there are actually, a little sneak peek there. There are actually many different ways that scientists make the prediction of whether or not the precipitation is going to be rain, snow, or a wintry mix. In this research, we took a closer look at all those different methods. And the reason that we were able to do this is because every report submitted by community observers acts as a concrete standard for comparison. So suppose, for example, that you were an observer here on the ground in Reno. You look outside to check on your dog and realize that, oh, hey, it's snowing. So you submit an observation. This automatically gives us a report of the location, the time, and the fact that it was snowing. And then, since we know where and when to look, we can use other tools to match up things like air temperature and humidity and so on. And all of these act as the ingredients that we plug into each model individually. Then each of those models is going to give its best guess, rain, snow, or a wintry mix. Well, you, the observer on the ground, told us that it was snowing, so we can directly compare whether or not the model got it right. And when we do this for every observation, we get a comprehensive idea of how well each of those models performs for a variety of conditions. So we did this process using observations submitted in the Sierra Nevada between fall 2019 and early 2021, which was about 2,200 observations. For reference, here's a map of the area. It's right on the border between Northern California and Northern Nevada. The types of precipitation phase partitioning tools that we looked at fell into 3 different categories: near surface meteorology models, tools that belong to the NASA Global Precipitation Monitoring Mission, and ground-based radar. So near surface meteorology models, they're pretty much exactly what they sound like. They make the prediction of rain versus snow based on the weather conditions happening near the surface. So those fell into 3 different types as well, which I've broken down here on the right: temperature threshold, temperature range models, and a binary logistic regression. In total, we looked at 14 different types of 14 different near surface meteorology models of those 3 types. The temperature threshold models each use a single cutoff point. If it's warmer outside than that cutoff point, the model predicts rain. If it's colder outside than the cutoff or equal to that cutoff, then it predicts snow. So we looked at several thresholds each for 3 different temperatures: air temperature, wet bulb temperature, and dew point temperature. Wet bulb and dew point are basically just 2 other ways of measuring the amount of energy in the air. They take into account humidity, unlike air temperature. Temperature range models function in a very similar way to temperature threshold models, except that if the temperature outside falls within a range of 2 air temperatures, it'll predict mixed precipitation. And finally, binary logistic regression, that's just a fancy way of saying it's an equation. It took into account both relative humidity and air temperature. For this research, we looked at 2 different types of tools that belong to the NASA Global Precipitation Monitoring Mission. One that uses a probability algorithm, and one that uses satellite data. You'll hear both Nayang and Haley mention the NASA GPM mission later on. And finally, we also looked at ground-based radar, which basically looks at precipitation while it's falling from the sky to measure where its properties change. So for each of those observations, we plugged in the associated variables to all of these different methods, and then we analyzed the results. What we learned was that overall, NASA's probability algorithm tended to overpredict rain. And at an overall glance, so did those near surface meteorology models, because the average snowfall prediction for all 14 was less than the actual snowfall frequency that was reported by the observers during that time period. But it's really important to note that there was high variability between those 14 near surface models, meaning that for the same conditions, they didn't all perform the same way. This chart on the right here shows that variability really well, so I'm going to take a moment to discuss how the chart's laid out and how it shows that there's a lot of variability. So first of all, you'll notice there's 2 main columns. That's because we looked at mixed precipitation in 2 different ways, and the results are shown side by side. On the x-axis here, we have air temperature in Celsius. On the y-axis, we have each of those near surface meteorology models: temperature threshold, temperature range, and binary logistic regression. So this chart is going to tell us how successful each of those models was at a given temperature. Darker colors on the chart, like that purple, that corresponds to low success rate, whereas brighter colors mean that at that temperature, the model tended to do a good job of predicting what the precipitation phase would be. So let's take a look. Notice that the darker colors, those low success rates, tends to be between about 0 and 10 degrees Celsius. From previous research, we actually expected this to be the case, but what's really important to note from this research is the fact that those colors are different within that little stretch there, especially that there's difference in the colors when you look at each column. So let's take a look at the between 2 and 3 degrees Celsius because it shows this variety really well. The fact that there's so much variety in those colors means that between 2 and 3 degrees Celsius, there was a lot of variety in how well all of those 14 different models performed. For example, looking at the temperature threshold, this is dew point one here, it had a lot higher success rate than the temperature range model, the darker purple one here. But there was actually a lot of variability even between models of the same type. For example, this air temperature threshold had a higher success rate than this air temperature threshold. But when we look back at all of those different temperatures together, we can really see that this was a common theme that there was variability within each of those temperature bins, so to speak, for that whole stretch between 0 and 10 degrees Celsius. Another really important thing that we learned from this research is that the models that took into account humidity tended to have higher success rates. And you can see this on the chart. In black boxes here, I've shown out the methods that consider humidity, those that take into account wet bulb temperature, dew point temperature, or relative humidity directly in the case of the binary logistic regression. Notice that those colors in those boxes are lighter. That's a direct representation of the fact that they had higher success rates. So why does it matter that we know how these methods tend to perform and the fact that they vary? Well, it helps us to make more informed decisions about which tools we use to predict if the precipitation will be solid or not. And it shows us that our current methods need a lot of improvement. Later on, Catherine will tell you why this is important for hydrology and for anticipating the impacts of storms on our society. This research tells us how well our tools describe the weather patterns that are specific to the Sierra Nevada, but the Sierra Nevada is only a very small area in the Mountain Rainier Snow's national scope. It's just this little bright point here. So in order to make similar analyses from areas where we have fewer observations, like the Cascades, we need the help of observers like you. Thank you.
Now that Sonia has showed us a comparison of a variety of different weather technologies, Ning Huang is going to talk about one of those. Sonia mentioned that we've looked at the NASA Global Precipitation Monitoring Mission, and this is what we're going to hear about next.
Thank you. So hi, everyone. Again, my name is Ning Huang, and I'm going to build upon what Sonia shared and talk more about how we use that satellite data and then develop snowfall probabilities. So I'm going to split my time in two parts. One, explain how we use the citizen science data and how that compares with similar data retrieved from satellites. And two, how we use citizen science data to better understand the probability of snowfall in regions across the continental United States. So to begin, we get data from what is known as the Global Precipitation Measurement Mission, also known as the GPM. This really neat constellation of satellites provides measurements on rain and snow. And the mission essentially can provide estimates for regions that lack on-ground precipitation measuring instruments, but also it can help us better understand precipitation dynamics. So then the data from the GPM is processed through an algorithm known as the iMerge, the Integrated Multi-Satellite Retrievals for GPM. And what we get from the outputs of that is the probability of liquid precipitation, which is measured from 0% to 100%. Now that you've heard me talk about probability like 10 times, I'm going to break that down, or that word probability, down for you. So you've heard of probability likely in the form of a percent when people talk about rain. So I quickly looked over at y'all's weather forecast, and it looks like there is an 80% chance of rain and snow on Saturday in the Mount St. Helens forecast area. So similarly, when we talk about the probability of liquid precipitation, we refer to a likelihood, a chance of something happening. But also, if you've played the game of what are the odds, you certainly know about this too. So going back to the probability of liquid precipitation, you can see on this gradient scale here that a probability close to 0 indicates snow presence, and closer to 100 indicates rain. And for the sake of this presentation, we use a 50% threshold, where the probability of liquid precipitation less than 50% is snow and greater than 50% is rain. Okay, so before we get started, I want to show you all this map of observations and the current regions we analyze. So the heat map here shows relatively how many observations from 2021 to 2022 Mountain Rain or Snow campaign we received. So seen in the dark red colors in the Lake Tahoe area, and then in the northeast, we racked over 4,000 observations at each location this year. So as for regions from left to right, we have the Sierra Nevada, the Central Basin and Range, Colorado Plateau, Southern Rockies, high plains, and then over in New England, the eastern Great Lakes lowlands and the northeastern highlands. Oh, it's not going. All right, so the general workflow to see how the satellites work is using both the satellite and citizen science data. So the citizen science data, again, being the truth of what is actually falling from the sky. And these go through several steps of processing to eventually output what we consider the satellite success rate. So this is a similar plot to what Sonia showed, but this shows the iMerge success rate by region. So we have, again, the air temperature on the x-axis in degrees Celsius, and the regions we just talked about on the y-axis. And we define success by the number of agreed phase observations by air temperature. So the darker orange colors indicate a low success rate, meaning the satellites did not detect the same precipitation phase compared to the truth, which is, again, the truth being citizen science data. And then you'll see at the lower and higher temperatures, the bins are lighter orange, meaning the satellites in your data agree. And this is observed across all regions. But then we fall into this close to 0 degrees temperature range where there's a ton of disagreement. So now that we answered objective 1, we'll move on to snowfall probabilities. So to do this, we only process the citizen science data from the 2021 water year to develop these probabilities. And the outputs look like this, split by region, with the probabilities expressed as % on the y-axis and air temperature on the x-axis, again in degrees Celsius. And in the points, we have observations summarized by temperature, and in the black line is the observations fitted to a regression curve. And it's kind of difficult to see how these differ by region. So we can actually superimpose all the fitted lines by region to end up with a plot that looks like this. So we still have air temperature on the x-axis, and on the y-axis, the snowfall probability. And we use a snowfall probability greater than 50% to indicate the temperature at which we will start seeing snow. So at temperature values greater than 50% snowfall probability, we expect to see snow. So particularly when we extract the air temperature at which the snowfall probability is 50% for each region, we can see that they all differ, with the highest being 4.24 degrees Celsius in the Southern Rockies, which is about 39.6 degrees Fahrenheit, and the lowest being in the Northeastern Highlands, 0.65 degrees Celsius, which is around 33.2 degrees Fahrenheit. We can hypothesize these differences being a combination of topographic and atmospheric factors, as Megan alluded to. But from this graph, we can agree that 0 degrees Celsius is not necessarily a good reference freezing point. So when we revisit the satellite success rate plot, I have in the black bars the 50% snowfall probability temperatures for each region from that previous plot in the past slide. And if we are using the 50% mark to be the determining line between rain and snow, we can assume values to the right of the black line are likely rain and to the left of the line likely snow. So with what we know now, we can better hypothesize whether the satellites were over-predicting or under-predicting rain or snow. So for example, in the Southern Rockies, the darker orange box to the right of the black line can mean the satellites were likely over-predicting rain. So I'll wrap up here to say that we can better understand satellite performance by using our citizen science data, but also as we analyze our citizen science observations, we are learning that regionally, the rain-snow line differs. So big picture, knowing what we know about these temperatures, they're so important because when we attempt any recreation in the mountains within this temperature range, around 0 degrees Celsius, the weather can be incredibly unpredictable. So what we're doing here in Mountain Rain or Snow is to solve this mystery so modeling efforts can predict better and also protect life and our resources. So thank you.
Wonderful, Nayan. Thank you so much. For those of you who are listening, we've now heard quite a bit about, we're going to drill in a bit more to the NASA Global Precipitation Measurement Mission And Haley is going to deepen our understanding of what that looks like for atmospheric river and non-atmospheric river storms.
Okay, sorry about that. I couldn't find the unmute button, but here we are. So yeah, hi, I'm Haley, and we are going to be talking about comparing the GPM measurement mission with mountain rain or snow observations for atmospheric river and non-atmospheric river storms in the Sierra Nevada. So as you've heard from all of our speakers so far, understanding precipitation phase, especially in these mountainous regions, are incredibly important. And obviously, it's a real challenge to accurately depict this precipitation phase measuring. So GPM is actively trying to increase their efforts to better predict precipitation phase. And having these observations is a really great standard to weigh GPM against in terms of those PLPP values. So I'm going to shift gears for a second. We're going to talk about what an atmospheric river is. You've probably heard them on the nose, but atmospheric rivers are storms that essentially just carry really great amounts of moisture from the tropics, and we get these really large extreme precipitation events. And you'll see things on the news like severe flooding and strong winds, mudslides, and that's exactly what's happening in California right now with that atmospheric river that just passed through. So we're going to be comparing those types of storms to non-atmospheric rivers, which are just your standard storm. So for our research objectives today, we're going to assess the measuring capabilities of NASA GPM for atmospheric river and non-atmospheric river storm types. And we're hoping to understand the GPM behaviors under these different precipitation phase conditions. So here's our study region. Again, we're going to be focusing within the Sierra Nevada region, pretty much in that Lake Tahoe area for the most part. And we're going to be focusing on two different storms. So one is December 22nd, and it is our atmospheric river storm. And the other is on March 19th, and that is our non-atmospheric river storm. And we're going to do this through three different measures. We're going to do it through an animation, a time series, and agreement statistics. So with the animation, it is a really great way just to visualize these two different data layers together. And we can observe any first signs of agreement and disagreement between these two different observing platforms of GPM and mountain rain or snow observations. Next, we're going to look at a time series, and this is just a really great way to see what GPM is reporting specifically over time and how mountain rain or snow observations are comparing to that value over time. So we're just going to observe that relationship. And then to do a more numerical approach, we're going to do the agreement statistics. So we're going to see how often do GPM and mountain rain or snow agree or disagree for atmospheric river and non-atmospheric river storms. So to do this, this is what you're going to see as we go through our animations. You're going to see this multicolored surface right here, and you're going to see a bunch of dots on this multicolored surface. So as Nayang expressed earlier, GPM measures these values in the terms of a probability. So we're going to just reflect on that idea again. So a value of 0 in this case is going to be snow, and a value of 100 is going to be rain. So for this animation, when you see a purple surface, that is GPM predicting that it is going to be snow. And when you see a red surface, that is GPM saying it's going to be rain. And then the same idea it happens with the dots. So these are our community observations being made. So when you see a purple dot, that is an observer saying you're seeing snow on the surface. And then when you see a red dot, that's a rain observation. And when you see a green dot, that's a mixed phase precipitation observation. So we're just going to see all of these in action. So I am going to share my screen with you. We are going to look at these animations. So here's the first one. This is our atmospheric river storm, and it is on December 22nd. It starts out as a snowy storm. You can see with this purple right here, and then it's going to transition into a much more rainy storm, and you'll see that with the change in the red down here. So here's the rain, and you can see red observations on the red surface, and that's really great. That means that GPM and mountain rain or snow observations are in agreement. We're seeing red on red, so that's really good, and that's really what we want to be seeing. But you'll see here in a second that mountain rain or snow are actually going to start reporting snow observations on the western side of Lake Tahoe before GPM starts reporting any signs of snow. So that makes us believe that there is some kind of delay in the measuring capabilities of GPM. So you'll see here now, everyone's reporting snow, but GPM's not saying it's snowing at all until now. So you're seeing that there's some kind of delay in the GPM measuring capabilities, especially for snow. But overall, this storm is really great for an atmospheric river. So there's a lot of agreement here. Next, we're going to look at the storm on March 19th, and this is our non-atmospheric river storm. So this storm shifts from rain to snow throughout, and we don't start to see observations until about noon. But with that, there's not a whole lot of agreement here. Just looking at this, you're seeing a lot of purple observations on red surfaces, and there's just not a whole lot of agreement there until the snow starts shifting in, and then we're starting to see those purple observations on the purple surfaces. So we're seeing more agreement towards the end, but there's definitely not a whole lot of good agreement there. So with that, all you really need to know is that atmospheric river storms seem to have a lot more agreement with mountain rain or snow observations. In terms of that non-atmospheric river storm, there doesn't seem to be a whole lot of agreement. So now we're going to shift into the time series. So essentially what I've done here is I've identified 4 locations in that animation that received the most observations from mountain rain or snow, and I'm going to compare that with GPM. And I got these plots and I'll explain how to interpret these. So what you're going to see is on our x-axis, we have time, and the beginning is the beginning of the storm, and the end, that's the end of the storm. Then we have our primary axis right here, which is the GPM PLPP values. And just to say it again, a value of 0 is snow and a value of 100 is rain. And then on the secondary axis, we have our community phase observations. So this is what people are observing over time. So GPM is saying, okay, it's snowing, it shoots up to rain, and then it goes back to snow. And then community phase observations kind of reflect that, right? You can see that when people are observing that it's rain, GPM is also saying that it's raining. And then when it shifts to that snow, you can also see that people are also saying it's snowing. And you can even see there's that kind of delay there where people are saying it's snowing first. But overall, this is pretty good, right? There seems to be a pattern between the GPM PLPP line and the community phase observations. However, on the non-atmospheric end, here are 4 interest locations, and here are those plots. You can see that there doesn't really seem to be a distinguishable pattern here. You can see that there seems to be a peak where mountain rain or snow observations are saying, hey, it's raining, and GPM's like, okay, yeah, it's raining too. But we're seeing a whole lot of different observations here in the middle too. So now let's look at this more a little numerically. We're going to look at agreement between these storms. So over here on the left, we have our atmospheric river storm, and on the right, we have our non-atmospheric river storm. And I divided this in 2 different ways. So we did the first statistic with just snow and rain observations. And then this second statistic was calculated with snow, rain, and mixed observations. Since mixed observations don't fall neatly in a PLPP value for GAPM, we included the mixed observations into the rain category. But to start without the mixed observations, we saw that the atmospheric river storm experienced an agreement rate of 68.47%, while the non-atmospheric river storm experienced 52.36% in agreement. So that's pretty low. But you can definitely see that there is a huge discrepancy between that atmospheric river and non-atmospheric river. And then when we include the mixed observations, we see that the agreement increases for the atmospheric river to 73%, and for the non-atmospheric river storm, it increases to 65%. So it's better, but it's definitely not great. So what does this tell us? We know that GPM has potential for measuring precipitation phase, and we can see that, but we can obviously see that it has better capabilities for measuring more moist storms. So when there's more rain rather than when there's more snow. So what's to come for the rest of this analysis? We definitely want to look at classification statistics. So that's just another way of looking at agreement and disagreement for these storms. We also want to move out of the Sierra Nevada and look at those other mountain ranges that Nayang and Sonia had shown you. And then with those observations and your help, it would be incredible to look at those other observations with your guys' added observations. So thank you.
Fantastic. Thank you, Haley. For those of you who are listening, we have heard a lot about the value of observations from individuals like you for the science and the technologies. Now we're going to hear from Catherine about how all of this work is moving the science forward.
Yes, thanks, Megan. Good evening, everybody. I'm Catherine. And as Megan said, I'm going to review some of the ways that all of this great research that Mountain Rain or Snow has been doing contributes to the broader scientific community. This isn't going to be comprehensive, don't worry. I'm just going to go through a few high points, but it should give you a pretty good idea. In addition, I'll also draw a distinction between how the scientific community is using it and how it will actually impact your lives. So starting with meteorology, obviously this is just one branch of the atmospheric sciences that could be using this information, but it's concerned with forecasting weather on short time horizons. What this means for you and for the scientific community is weather forecasters can rely on this information in order to help inform those forecasts, but also to educate the public. So for example, not only are you getting hopefully better forecasts, but I don't know if you've ever seen some of the diagrams or some of the animations that they've used to explain the phenomenon that we're talking about. Those will be informed and come directly from the sort of research that Haley, Sonia, and Ning Huang have just explained here. And as they've demonstrated, the results from the project help to validate and improve the measurements, like those coming from NASA satellites. Now, the impact to you, to all of our daily lives, is wide-ranging, obviously, from simply knowing what kind of precipitation to expect, which can help with transportation in all of its forms, to the delivery of goods and services, and to making winter sports safer, among other things, by better informing emergency managers of extreme weather conditions, like you might find in avalanche areas. The science of hydrology is actually concerned with what happens to the water once the precipitation has hit the ground. The form that that precipitation takes actually affects the water content, the infiltration rates, and other aspects that aid in managing water resources at large geographical scales. And the more that we understand about precipitation partitioning, the better our methods for measuring and predicting water budgets. Now, while the agricultural sciences both rely on the meteorology and hydrology I've just discussed, it is a discipline of its own that actually benefits from mountain rain or snow research in its own specific ways. Farming itself has evolved to more sophisticated methods in crops. The type of precipitation can be as important as the timing and the quantity. And responding to weather events with certain types of precipitation can help farmers respond with the appropriate actions that can be crucial for preventing things like losses due to frost. What you're looking at here is actually a vineyard, and they are taking, looks like very old methods, but they're very tried and true for helping them to deal with frost. Now, plant pollinator interactions can be very sensitive to temperature, but they can also be really sensitive to different forms of precipitation. This can also affect not just crops in the short run, but obviously long term. Many scientific disciplines, in particular the ones I've just discussed, depend on computer science to model the physical world. The more data that's collected, the more advanced computer models have become. The image you're looking at here is actually from the US Air Force, and interestingly, they're collecting data on atmospheric rivers, like Haley mentioned. Now, machine learning and artificial intelligence methodologies take in a lot of data, and they need this data in order to improve the model skill and the predictions. Now, observations like those from the Mountain Rain or Snow project are really crucial for providing a lot of that data. Finally, the type of projects like a community or a citizen science project like this is an observation based and community based project that allows us the opportunity to improve social sciences. It will help to answer questions like, what is it that motivates people to participate? How do we best engage communities to take these voluntary observations? What is it we as a scientific community owe these communities, and what is it that they would most like to get from us? The particularly in a project like this, can help to improve future citizen science projects. So I'm going to send it back to Megan, and she could talk to you about how you could participate in the Mountain Rain or Snow project going forward.
Catherine, and thank you everyone who is here with us. Right till the end, we are going to do Q&A in just a minute. As soon as I share a little bit about how you can get started with Mountain Rain or Snow. So we've been talking all about how people from coast to coast, you saw this figure earlier with Ning Huang. We've been talking about how people from coast to coast have been sending us these really valuable observations. And now we invite you to join us and get started. So this, like Ning Huang mentioned, is a heat map of where our observations came last winter season. There were 15,000 of them that came in between November and the end of April of last year. And to date, I just checked a few minutes ago, to date for this season from November till January 19th, we've had 8,700 observations submitted this season already. So we are doing so well, and we really hope that the Pacific Northwest can put itself on the map for this season as well. So our project is pretty unique in the community and citizen science world. We communicate with all of our observers via text message. And the way to get started is to find your region. So I'm assuming most of you are going to be here in the Pacific Northwest. And you find the keyword that's associated with your region. So you can get out your phone and you can open your text message area and just type in those 3 little letters, PNW, and text them to our project number. And when you text that keyword to our project number, we are going to send a series of short text messages that explain how to participate. And they're going to send the link to the web app. It's an app that functions through your phone's browser. And they're going to send a link to that web app for you to submit those observations. So why do we have you send us a keyword? That's so that we can send weather alerts when a storm of interest is on its way. So this weekend, it sounds like there's going to be a mix of rain and snow in your area. That's an ideal opportunity to track the weather with us. And so we would send out a little alert that says, hey, there's some precipitation on its way. It's really important for the science. Here's how you can send us observations. If you are tuning in from somewhere that isn't one of these regions listed, you can text the word weather to that same number, and you'll get periodic alerts that aren't related to weather, because that's our kind of general list, but they are invitations to continue to participate. Last year, we showed you that heat map a second ago. Last year, we had 4 regions involved in the program. Now this year we've doubled it to 8, as you can see, and we're really excited to have more people from more mountain ranges in a greater hydroclimatic diversity taking part. So once you text the keyword to the project number, you're going to get, like I mentioned, a link to the web app, and it's going to open to a little portal that looks like this. And this is going to be your way to send observations. So you can sign in with your username, create a password. The key is to make sure location services are enabled. So if you're a person that turns them off, you can just turn them on when you're going to send us a report. And you've heard me use this term web app a couple of times. It is an application, just like one you would download, but it functions through your browser. So it's a lot more nimble. It requires a lot less updating. So it's a pretty cool, technology. This is our main screen. At the bottom, you can see those series of tabs. There's one that says submit. The question, and this is the question that we opened the presentation with, what is falling from the sky right now? We are asking people, like we said, to send us real-time updates anytime it's raining, snowing, or a wintry mix. So if you notice that it starts precipitating or that the precipitation phase changes, send us an observation. Some people like to set a little timer every 30 minutes throughout a storm event to give us updates on what's falling from the sky. We often get questions on what is mixed precipitation. It might be kind of heavy, wet, heavy wet snow that looks like it's melting, or it might look like rain that's crystallizing. If you have to look at it twice, it's probably mixed precipitation. And then finally, you can navigate to the reports that you've already uploaded, read about the project, or update your profile at the bottom. So I'm going to just click back to that screen. We welcome you to participate. We would really love to hear from you at any point. In the when you receive a text message, you can reply directly to that message and you reach one of the project team members. You can ask us questions, you can ask for more info, you can tell us about how much snow has fallen in your region. And we also invite you to check out our project webpage, which is www.rainersnow.org, or email us if you have questions for any of us. Feel free to send me an email or shoot us a text and I will get it to any of our team members. So with that, we would love to take your questions.
Awesome. First of all, thank you so much for that presentation. It was really interesting stuff. And I will add that contact information that you posted to our chat feed after the event. Let's see. Okay. So how long have you been doing this, and have you seen any warming trends over the years?
That is a great question. That is a really thoughtful question. So we started this project in the winter of 2019. We didn't explain the history, but we started in the Sierra Nevada region, just one little region. And then last year, like I mentioned, we grew to 4 and now we're growing to 8. We do not have enough data to track climate warming trends, but as our hydroclimatologist will tell you, if this project goes on for many, many years, it has the potential to track regional patterns of rain versus snow, as well as storm by storm on a storm by storm basis. Does anyone else want to add potential for how this project relates to climate change? Okay, cool. So it sounds like that summed it up, but yeah, that is a really great question. And I'm glad your audience is thinking about that because it is on our minds too.
Great. Yeah. And then, so my personal question that springs from that is, you've been doing this since 2019. Have you seen any trends that have surprised you or kind of jumped out at you in that time?
Well, Nayang was describing some of the differences between regions, and maybe she can drill into it a little bit more. There's been some really cool phenomena that appear on a region by region basis.
Yeah, I like to talk about that. I don't know if y'all remember that plot that I showed where it had all the different regression curves plotted by region. And I mentioned that the Southern Rockies had a threshold as high as 39 degrees Fahrenheit. I don't know for you, but for me, that's pretty shocking. Because really, whatever I learned in school, in grade school, was that 0 degrees Fahrenheit is always the freezing point. That's when we're going to start seeing snow. But actually, I'm actually based in the Rockies. And so what I'm now realizing is, okay, maybe 39 degrees is when I should start seeing, or when I should start worrying about whether I should be on the road or not. So yeah, I think that's the coolest part about how region by region it differs. And hopefully with more observations, we can then provide that those threshold values, or even just more of the data to people that actually will then implement it into models, and then that will actually then help you guys, everyone out.
Great, thank you. So recently, I think everyone in the country was impacted by this huge winter storm over the holidays, and you were talking about atmospheric rivers and storms that aren't. Now, I was curious, like, was that a culmination of several different factors? Is there a giant atmospheric river that just converged and dumped snow on us? Can you talk a little bit about what led up to that?
Yeah, I could talk a little bit about it. So I haven't looked into it too much, obviously, but it seems like, so atmospheric rivers, they have varying magnitudes. So that's why you'll have these really small atmospheric rivers and they just seem like standard storms. So that's another thing I'm looking into, is just looking at these atmospheric rivers that aren't as aggressive. But then you do have these storms where they come in and just like hell's blazing, rain all over the place. So yeah, it really just is dependent on the amount of moisture that storm carries up from the tropics. So yeah.
Okay, cool. Now, I'm going to go download this app and start sending you updates. And some other people had this question too. Is there such a thing as too much data? Am I going to annoy you? Are you going to email me and tell me to stop?
No, there is no such thing as too much data for this project. It's actually really, really helpful if you send us what us nerds like to call longitudinal observations. So observations that happen at regular intervals over a period of time or over a period of space. And there was a really great person, I don't know who they were, but they were in the Pacific Northwest and they must have been traveling down, I think it was I-5, and they sent a series of observations at regular intervals, and you could just see it. We've got a map on our database, and you could just see this nice, beautiful trail of observations along the highway. That's the kind of thing that either through time or through space are really helpful. If you happen to be driving in some weather as you go up in elevation, that's another great opportunity to provide a snapshot of what's going on.
Right. Okay, final question here. Do you have any plans to expand beyond the United States?
I love hearing that. So this particular project, this funding is coming from NASA. You might have guessed that partly based on the logos that appeared on some of our slides, but also the fact that we're focusing on NASA satellites right now. Now, those satellites do circulate the entire globe, which is great. Last year, when we launched our coast to coast kind of like continental US regions, we had the NASA HQ put out some like tweets and social media stuff. And we have people in Canada and India and Nepal and Greece sending us observations of what's going on the ground. We don't actively have weather alerts that go to those regions. There is no reason why down the line we can't include more. It would increase the hydroclimatic diversity of the project and would be super valuable. And right now it's just about growing at a sustainable pace so that the people and the scientists can work together in a nice rhythm. So the sky's the limit. That's the short answer.
Great. I'll tell my cousins in Canada to download the app too. Thank you. Well, thank you all so much for being here. And we will be doing Views and Brews again in March, and that one will be in person. And you can check our website out for details. Thank you.